Okay, so I work for Kinetic. I'm a systems electropropulsion systems engineer. I've been working in EP for just over 10 years, and I used to work on Hall effect thrusters, but then I switched, and I've been doing gridded ion engines for the last 4.5 years. So I'll talk to you a bit about that. So I did draw the short straw because I have the talk just after lunch, which is probably the worst one. So I'll just try and make sure that you don't fall asleep. I'll do my best. So a brief outline of the presentation. I'll start by explaining what a gridded ion engine is, give you a bit of background on EP and why we use electric propulsion. I'll try to skip a bit because you've already had a few presentations. And a lot of the speakers have already talked about what EP is and how it works. So I'm not going to repeat everything. Okay, but before I start, I wanted to show you a short video. So I'm not sure there's a sound, but there are subtitles, so you'll be able to understand it. So it's a little video from Star Trek. Yeah, no, there's no sound. So you have to read the subtitles. Okay, so there you go. It does give it a little twist without the sound. It's a bit strange, but anyway. So the reason I wanted to show you this is, well, first because it's quite fun, but also because Scotty does get it quite wrong, because this is supposed to be in probably 2 centuries, and clearly we have electric propulsion now, but even in '68, when this episode was done, we already had electric propulsion, okay? So proof of this is this infograph, which I quite like. I hope you see it, but you'll understand why I like it anyway. So this is from 2008. It was done by Aerojet, and what it shows is the operational satellites that use electric propulsion. So you won't be able to read, but it does show all the satellites that operate with EP, not only Aerojet. And the cumulative number of satellites using EP in 2008 was 226. So that was before all this new era of application that we've been talking about came along. So it was already quite a big number. So it's not science fiction at all. It's very real. So a few words about the history of EP and gridded ion engines in particular. Some people have already talked about it. So EP was really mentioned for the first time in the 1900s, 1906, 1911, by Goddard and Tsiolkovsky. So they're what we call the fathers of electric propulsion. But at the time they only mentioned the fact that you could use electrical power to accelerate particles. There was no atom model at the time. It was very, very vague. So you have to wait until all the physics coming into plasma physics, atomic physics, in the start of the 20th century. And then you get to the 60s with Stirlinger, who published the ion propulsion for space flights, where he actually there details how you could use electric propulsion to accelerate ions, electrical power to accelerate ions, which is really the basics of electric propulsion. And then in the 60s and the 70s, you have the first thrusters that start flying. Basically, you had gridded ion engines in the US and Hall effect thrusters in the Soviet Union. And during all those years, 70s, 80s, mostly in the Soviet Union, electric propulsion was used for station keeping. You do have to wait until 1994, where the first gridded ion engine was launched for station keeping use. That was a Japanese thruster. And then you have Deep Space One, which is the N-Star, Rincos gridded ion engine. NASA mission, and then Hayabusa in 2003. I didn't put Artemis there, which was in 2001, and then Goche, so T5 kinetic thruster, ESA mission, Baby Colombo is coming along. And then, as you've heard earlier today, Vincent explained it quite well, and Jose. In 2012, you had Boeing announcing that they were going to develop and build an all-electric Boeing platform, which would not only enable station keeping, but also orbit transfer for geostationary satellites. And after that, everyone got into the party, and Airbus has now Eutelsat, which did the orbit raising, the first European orbit raising using EP a couple of weeks ago. So this gives you an idea of how everything evolved. So why would you use electric propulsion? So again, it's been explained, but I'll just go through it quickly, and go really to the basics of propulsion, whether it's electric or not. When you look at a propulsion system, what you want to look at is the conservation of momentum. So you take your spacecraft that has a mass and a velocity, and you follow the evolution of that system in time. And what happens is that in the delta t, you'll have an ejection of particles, and what you want to make sure is that you conserve your momentum. So that's sorry, I have a cold too, which doesn't help. Okay, I can't. Oh, anyway. If you write the conservation of momentum, you get that the mass of the spacecraft times the delta v, so the increment in velocity, is equal to the velocity of the ejected particles of the propellant times the variation in mass. Okay? So you can integrate this between an initial and a final time, and that gives you what we call the rocket equation, or the Tsiolkovsky equation. And, gracias. And you get this. Now this is really important, and why is it very important? Is because it tells you that the delta V is directly proportional to the ejection of the particles. Now, you can see this in two ways. You can either say, okay, well, if I increase my ejection velocity, I can have access to delta V's, which are much higher. And that's what happens with Baby Colombo, for example. You can afford doing missions that otherwise you wouldn't be able to think of. But you can also see it the other way around, so more in the commercial side. Say, okay, well, I've got a fixed delta V for my mission. If I increase my ejection velocity, I can reduce my dry mass because I can increase my dry mass, but because I'm reducing my propellant mass. Okay. So this is really why everyone's so interested in electric propulsion, because it gives you ejection speeds that are at least 1 order of magnitude higher than what you would get with chemical propulsion. Okay? And really, the key to that is that, from a very simplistic point of view, when you have a chemical engine, a chemical rocket, your ejection speed is always going to be limited by the energy contained in your chemical reaction. Okay? And that's usually 200-300 meters a second. That's the maximum you can get. And you have to store that energy in the propellant you carry in the spacecraft. What you do in electric propulsion is that you only need less propellant, and you can use the solar energy to inject into the propulsion system and use it to accelerate the particles. So that's really the key fundamental difference. Okay. So there's different types of electric propulsion. The classic categorization is this one, is electrothermal, where what you do is not ionize the propellant, but you use electrical energy to heat up your propellant. So those are arc jets and resistor jets. You have electrostatic types, where what you do is create a plasma and use an electrostatic force to accelerate the ions. So in there you have gridded-on engines, FEEP, electrosplay or colloids. And then you have electromagnetic thrusters, which use an electric field and a magnetic field. So heads, so Hall effect thrusters, they're a bit in between, really, because you do accelerate the particles with an electric field, but you use a magnetic field in the process too. And then you have MPDs and PPTs. So I just put a table here. This is taken from Goebel and Katz's EP book, which is quite a good reference for any electric propulsion. And it just gives you an idea of the different ISPs and input powers that were required. So again, specific impulse, it's been explained. It's proportional to the ejection speed. So it tells you how efficient the system is in terms of fuel efficiency, okay? So you see the difference between chemical and all EP. And you also see that ion thrusters, so these are gridded ion engines, have the highest ISP. So they're the most efficient in terms of fuel efficiency. So how does a gridded ion engine work? So this is Kaufman, which gave his name to one of the types of thrusters. That's why I chose to put his picture here. So really, you're looking at three processes: ionization, acceleration, and neutralization. So if you look at your propulsion system, you have an input, which is the propellant and the electrical power. And then what you do is you take your propellant, you ionize it, so you create a plasma. You've had a lecture on physics of plasma, so you know everything about it now. And then what you want to do is take the ions from the plasma, accelerate them. That creates the thrust, which is really the output of the system. And then because you're extracting the positive charges from the spacecraft, you have to neutralize that, because otherwise you would be charging your spacecraft and you would get to a point where it would be impossible to extract charges, okay? So that's the neutralization. And the output, as I said, is thrust, which is approximately the mass flow of ions multiplied by the ejection speed of the ions, okay? And the way we characterize the efficiency of the system is using this formula. So this gives you the total efficiency. So this is the square of the thrust divided by 2 times the mass flow of the propellant times the total power. So this is the equation, but what this really gives you is it tells you how much of the power that you're putting in the system is converted in thrust, which for propulsion is what you want. Okay, so I'm going to go through the 3 processes. The first one is ionization. So it's maybe one of the tricky ones to explain, just because when we talk about gridded ion engines, the commonality is always the grids, but you have a wide family of gridded ion engines, and the type of thruster is defined by the type of ionization you do, okay? Okay, so what you want to do is ionize the gas, is create a plasma. So really you could do whatever you want. As long as you create a plasma and have ions in there, you can think of anything. Now, normally we always have, so you saw this morning this plot of the different types of plasma with the temperature and the density. So we always have similar types of thruster, plasma, in EP. It's always a cold plasma, so that means that the electron temperature is relatively low compared to other plasmas. It's low pressure, so we always operate in vacuum, and it's non-equilibrium. So what that means is that the electron temperature, so the energy of the electrons, is much higher than the energy of the ions, okay? So, as I said, you could think of any plasma generator you want to ionize the gas, but really there's 3 types that have survived time. There's what we call the DC discharge, sometimes called electron bombardment. There's the RF inductive discharge, and then there's the microwave discharge, or the electron cyclotron resonance discharge. So I'll go through all of those. I'll insist a bit more on the DC coupled discharge, because that's what we do at Kinetic, and that's the thrusters we build. And also I know a bit more about those. So I told you about the total efficiency earlier. When you look at the ionization process, the two efficiencies you really want to look at are the mass utilization and the discharge losses. So the mass utilization is the beam current, so that's the current of ions you're extracting from the chamber, times the mass of the propellant, so xenon, divided by the charge, and the mass flow used in the discharge. And then the discharge loss is the discharge power divided by the beam current, so the ion current you're extracting. Now, what do they actually mean? So the mass utilization tells you how much of the propellant you inject in the discharge chamber you're extracting. So, well, it's in the name, how much are you utilizing? And the discharge losses tells you it's sometimes called the ion cost. It's how much power you need to extract one ion. So the mass utilization, you want it to be as high as possible. The discharge loss as low as possible. So you want it to be as less costly as possible. Now, it is tricky, so I put an example of a plot here with a discharge loss against the propellant utilization. So what I was saying is that really you want to operate at the maximum mass utilization, but the lowest discharge loss. The problem is that if you increase the mass utilization too much, then the energy of the plasma, the energy of the electrons, is going to be very high. And then you're going to start to have more losses. So there's often a sweet point here where you want to work at, and which is the point where you design your ionization chamber. Okay. Just a quick word about propellant. So as you know, almost everyone uses xenon. Originally, a lot of the thrusters in the 60s, 70s used mercury for the same reasons as we use xenon now, because it's easy to ionize, it's heavy. Now the difference with mercury is that it was not as easy to handle, and also it caused a lot of contamination issues on spacecraft. So we decided to move to xenon, but the problem we have with xenon now is that it's becoming very expensive, as you heard this morning. So a lot of people are looking at other propellants. Okay, so the DC discharge then. So this is called electron bombardment, and it's called electron bombardment because so to create a plasma, what you have to do is give energy to the electrons. So there's different ways you can give energy to the electrons. What you do in this case is provoke collisions. So you have a bunch of neutrals in your chamber, you have an electron gun that creates electrons, and what you do is apply a voltage difference between a cathode and an anode, and that pulls the electrons, and that causes collisions with the neutrals. And when you have a collision, the electrons that's colliding is going to give energy to an electron in the atom, and that's going to ionize. Okay? And so that's how you start the discharge, and you have a discharge avalanche, and at some point, you have a plasma which has a fixed potential, and which sits between your anode and your cathode. Now, in all these thrusters, what we do is use a magnetic field just to confine the electrons. So what you do when you apply a magnetic field is that you trap the electrons. So they're not as fast anymore. And if they're not as fast, it means they can do even more collisions. So that sustains the efficiency of your discharge, and you have plasma densities that are higher, which means that you can also extract more ions. I just put some numbers here to give you an idea of the plasma parameters. And really there's two variants that we still use of these. There's what we call the Kaufman configuration, which we do at Kinetic. We've been doing. We're going to do a ring cusp thruster now. And then there's the ring cusp configuration, which historically has been used in the US for the last 20 years, I think. And the only difference, the main difference between both is the magnetic field configuration. Okay. So in the Kaufman configuration, what you have is a cylindrical anode, so it doesn't cover the whole discharge chamber, and then you have a very divergent magnetic field that attaches from here to the edge of the baffle to the limit of the grids. Okay, so you see here an electron that's coming out of the cathode, that's trapped, and that eventually will go to the anode. Okay. So in our thrusters, we have a baffle also at the end of the cathode. That's the main reason for that is to flatten the plasma density. I'll say maybe something about that later with the grids. That's just to have a flat profile so that you extract the same amount of ions throughout the grid. So in our thrusters and Kaufman type thrusters, the magnetic field is normally generated by a solenoid. So the drawback of that is that you need a power supply to power the solenoid. But the advantage is that you can very finely control the magnetic field in the discharge. And when you control finely the magnetic field, you also control very finely the plasma density, and so also the thrust, okay, which is one of the key requirements for GOCHE and the T5, like Jose explained this morning. So I put a few examples of Kaufman thrusters. These are all kinetic thrusters. So the T5 here, which was a 500 watt, is a 500 watt class thruster. So you had two of these on GOCHE. It was only for redundancy. They only needed one, but in case there was a failure, the other one could be used. So the first thruster actually never failed. It fired for over 36,000 hours. That's about, I think the mission was 4 years, you said? 4 years? And what they did at the end of the mission was turn on the second thruster to see if it worked or not, and it did work. It had nominal performance, so that was quite a good result for us because after not having been used for 4 years, it was quite good. So the other thruster is a T6. We're not very original with the names. It's a bigger thruster, same principle. And it's the thruster for Bepi Colombo, which is due to be launched at the end of next year. So this is a 5 kilowatt class thruster. It produces up to 145 millinewtons. ISP is just under 4,000 seconds. And we have 4 thrusters in Bepi Colombo. Now in this case, they needed to fire 2 thrusters at the same time. So you have 4 for redundancy, but you have 2 firings simultaneously. And here's a picture of the 6 thrusters being integrated at ESTEC for the spacecraft. Okay, I think I have to speed up a bit. So the other version of the Electron bombardment thruster is the ring cusp configuration. It's very similar. The main difference is the magnetic field. So you have a set of magnets that generate these cusps here that do the same job. And then the other difference is that because of this magnetic field, the anode in here is not just that cylindrical bit, it's the whole discharge chamber. Okay? So the advantages of this configuration is that the discharge overall is more efficient. So you'll get more thrust for the same power. The plasma profile, as I was saying earlier, is flatter, and you don't need a power supply to create the magnet. To create the magnetic field. The drawback is that it's less flexible than a Kaufman, but that's something you might not need, for example, for geosatellites. We did need it for GOCHE because it was a very specific mission, but that might be just a one-off. Okay, so a few pictures of ring cusp thrusters. As I said, they're mostly American. So the N-Star is probably the most famous one with the zips. So this was the thruster on Deep Space One, Deep Space American mission. So it was also the thruster on Dawn, another Deep Space US mission. There's a new development, a bigger thrust called the Next, also NASA. And then there's the ZIPS, which is used by Boeing on their commercial platforms. So a few words about the other types of ionization. I think there's a lecture after on RF, so I'll go very quickly. And also I don't have a lot of time. So really on RF thrusters, what you do is that instead of having a cathode and relying only on collisions, you apply a RF wave. So you apply an RF current on a coil that's wrapped around the discharge chamber. That generates a magnetic field, and because it's AC, that's going to generate an azimuthal electric field, and that field is the field that gives the energy to the electrons. So if you didn't have any collisions, because it's AC, you would just give and take energy, but because you have collisions, you sort of randomize that if you want, and you heat up the electrons. Now, one of the difficulties in RF thrusters is that at the start, you don't have a lot of electrons. You only have 3 electrons in vacuum. So you have to find ways of igniting them, but it's more than feasible. There's a lot of developments of RF thrusters in Germany. All the RID series with the RID 10 that flew on Artemis are based on this system. So it's just another way of doing it. The other ionization process that I wanted to present is microwave. So what you do here is similar to the RF. You inject a wave, but it's a much higher frequency. It's in the order of the gigahertz. And what happens here is that you apply a magnetic field. And you remember I said when you apply a magnetic field to electrons, they're trapped. So they have a circular trajectory. What you do here is that you make sure that the frequency of your wave matches the cyclotron frequency of your electron. So then the electron is in resonance, and then it starts gaining energy because it always sees a fixed electric field. And you can have the same problems for ignition, but again, that's a problem you have a solution for. The most famous, so it's not the only ones, but the most famous thrusters that are based on this concept are the Japanese thrusters, which flew on Hayabusa. That was an asteroid mission, and Hayabusa 2, which is flying right now. Okay, so let's go to the acceleration now. So this is really important. It's probably the most important bit. So I'll try to take my time. So what you want to do once you have your plasma is take the ions out, but also accelerate them. So the way you do that is apply a high voltage so that you rise the electrical potential of the ions. So you could just do that and see what happens. But then if you just do that, the plasma is just going to diffuse, and you're not really going to have a focused beam or a thrust. So what you do is stick a grid in front of the plasma with a hole. And now, so I didn't want to put too many equations, but this one is, of any, this is the one you have to know. So this is a Langmuir equation. And what it tells you is that when you put a surface in a plasma that has a potential that's very different from the electron energy, you have what we call a sheath. And what that is an area where there's a space charge. So a plasma is normally, well, in our case, the electron density is approximately the ion density. What you have here is that close to the area where you're applying the potential, the electron density is almost zero, and the ion density goes up. Okay? But what's very important is that there's a limitation on the current density that you can extract. And that limitation depends on the potential you're applying and on the sheath thickness. Okay? So you apply that potential to the surface, you have this potential drop. But then if you only do that, sorry, I'll come back, you would also have ions that are very energetic that would be hitting your grid. And that grid will last for, I don't know, maybe 50 hours, which is clearly not enough to go to Mercury. So what you do is put another grid, which is called the axial grid, the screen grid. And what that does is exactly that. It screens the plasma from the axial grid. Okay? So it focuses the ion. I have another slide on that after. But its main role is to do that, is to screen the plasma from the axial grid. So you have this potential drop that the ions follow. The last thing you want to do is, because, as I said, you have to neutralize the beam. So at the same time as you're extracting ions here, you also have electrons that are coming into the plume. Now, if the electrons see a positive potential, they're just going to go back to it. Okay? And you don't want to do that, because then you're having an electron current coming in, which for you looks like an ion current. So the efficiency is very poor, so it's not great. So what you do is apply a negative bias to the axial voltage to repel the electrons here. Okay? Now, it doesn't change the overall potential drop. The ions eventually are going to be accelerated to the same speed, because the potential drop they see is the difference between this potential and this potential. Okay. Okay, so this is really the basics on acceleration. There's cases where you can add more grids to avoid these problems. Well, to avoid axial erosion, you can add another grid here just to protect the axial grid, or you can even think about having lots of these couples of grids and adding one after the other. So you have a thruster called the DS4G, which did that. It was invented by Dave Fern from Kinetic. And what that does is, because you have a limitation from the Langmuir Law on the amount of current you can extract for a given voltage, you just split the voltage across several grids. And then you can extract even more current. Okay? Now, the problem with that is that it's very nice on paper, but it's very difficult to manufacture grids. And from an engineering point of view, especially for vibration and alignment, it's not an easy thing to do. So 2 grids is already quite challenging. So coming back to this Langmuir Law, really what you want to do when you design a grid is design it sorry, so that you maximize what we call the pervariance. So the pervariance is a parameter that we use a lot. It's the beam current divided by the potential difference between the grids elevated to 3 seconds. I don't know how to say that, actually. And when you have round apertures in your grid, this is the equation you have for the maximum pervariance, where small d is the distance between the grids, and the big D, the large D, is the size of the hole. Okay? So you want to maximize the pervariance, because then you can extract more current for a given voltage. So what you want to do is first have an aperture size that's smaller than the distance between the grids, but also have a distance between the grids that's as small as possible. You can see here that it's in the denominator, so the smaller the distance, the better. Now, if you don't operate close to the pervariance parameter, what you have, sorry, is this here. So this is the ideal case. So this is an ion trajectory. You can see that it follows nicely the electric field. This is very much like optics. There's a huge parallel with normal optics. So it's very useful to think about optics when you think about grids. We often talk about grid optics anyway. So the ion is extracted like this and is accelerated. If you change the sheath here in the discharge, so if you operate at under pervariance, your sheath is going to get closer. Okay, so it's exactly as if you were changing your lens on an optical system. So the focusing of the ions is going to be different, and eventually you're going to start hitting your grids. And then you have the same problem I mentioned earlier. Without the screen grid, you have ions that have over 1 kilovolt that are hitting your grid, which is not going to last very long. And you have the same problem if you go over pervariance, where your sheath is even bigger, and then you're also defocused, but you have a cross, you cross actually the beams. Okay, I wanted to touch quickly about lifetime. Now, I wanted to talk about this because it's a common problem that anyone will have with any plasma thruster. As long as you have a plasma, you will have erosion. Now we have grids, so we'll have erosion on the grids, but if you have a ceramic channel, you have erosion on the ceramic channel. That's, I mean, plasma is widely used on etching processes, so it's not a surprise. So there's different types of grid erosion. One of them is screen grid erosion. So this is the ions in the plasma that have some energy and hit directly the screen grid. So what you want to do to avoid that is operate at energies that are not too high. Okay. The other one, which is often the limiting parameter for thrusters, is the axial grid erosion. Now, when I say it's limiting, it's a problem, but it doesn't mean it's a problem we don't solve. I mean, Gautier ran for 36,000 hours. On BEPI, our thrusters are supposed to run over 10,000 hours. I think it's Next that's done, or INSAR, I can't remember, 40,000 hours. So it's a problem, but you can still live with it. So there's two types of axial grid erosion. One of them is pits and grooves. So pits and grooves comes from charge exchange ions. So charge exchange ions are an ion that's being extracted from the grids, hits a neutral, because you'll always have back pressure of neutrals in a thruster, and it exchanges its charge. So the neutral becomes fast, and the ion becomes slow. Now the problem is that just after the axial grid, so just after the grids, if the ion doesn't have a lot of energy, it's going to see the negative potential and is going to go back onto the axial grid. So it's going to gain maybe 50, 100 eV and hit the axial grid. So this is what's schematically shown here. And this is a picture of the sort of erosion you can have on the grids. So we call them pits and grooves because you have grooves in the area between the holes and then pits in the intersections. Now the other type of erosion you can have is also caused by charge exchange ions. It's bore erosion, and it's where the apertures of the axial grid become wider, okay? And that's because in this case you have charge exchange ions that are created in the intergrid section. So instead of following the nice focused beam I showed you earlier, they're defocused and they hit the edges of the apertures. So you don't want that too. The problem here is that if your apertures are too big, the potential in the center of the aperture is going to be much higher than the voltage you apply to the grid. So eventually, you could have an electron coming back in that way. So as I said, it doesn't mean that we can use these thrusters. Obviously, we use them for thousands and thousands and thousands of hours. The approach we have to all this is either by test, but also by modeling. So what we try to do, because life tests are so long, what we try to do is do endurance tests, which are shorter, and then use those endurance tests to validate our erosion models, and then we can extrapolate to the lifetime of your mission. So just a few pictures of some grid sets here. These are the T6 grid sets. So these are 22 centimeter grids. And this is quite a fun picture of a 57 centimeter grid set. Now again, coming back to the engineering, you could do a grid that's the size of the room, but then when you come to vibrate it, you have to remember that the distance between the grids is in the order of 1 millimeter. So that does put things into perspective in terms of the engineering problem you have. Okay. So I don't know how I'm doing with time, but 5 minutes? Great. So a quick word on neutralization. Now, neutralization, it's not specific to gridded ion engines. You need it for Hall effect thrusters. You need it as soon as you extract an ion beam from a thruster. You need electrons to neutralize them, okay? Now, for the first thrusters, people tended to use hot filaments. So that's just like a light bulb. You can just take a light bulb, run a current through it, and that's going to emit electrons. It's very easy. I put a picture here. This is actually a picture from a RIT thruster tested at ESTEC with a light bulb that was bought and that was used to neutralize the beam. Now the problem with that is that they had a lifetime that was very short. They would only last for a few hundred hours because the filament would just burn out. Now the most common way of doing neutralization now is to use hollow cathodes. So we've been building hollow cathodes for, I think, 40 years. It's a technology that actually came from cathode tubes. We inherited from Philips. And the way they work is, is that you have a cylinder, and what you do is that you start by heating the cylinder, like the filament, so that it starts emitting electrons. So you have that at around 1,000 degrees Celsius, okay? Now, when you start having an electron emission, you apply, exactly as I explained for the DC thruster, you apply a voltage difference, and you generate a DC discharge within the cylinder. And then what happens is that because you're bombarding your surfaces in the cylinder, you're emitting electrons in that way. So you don't have to use the heaters anymore. The discharge is self-sustained, and you produce an electron current. So what you have to do that, though, is to use what we call a low work function material. So that just means that it's a material that's going to emit electrons very easily. Now the most common ones are barium oxide and LaB6. All of our cathodes are barium oxide, but there's a trend now towards LaB6. The reason for that is that with barium oxide, you have to be careful with what gas you put in there. If you have oxygen, you can form oxidized layers on the inside of the cathode, and that's gonna increase the work function of the material. So you're not going to be able to emit electrons as easily, and the discharge is not going to be efficient, or you might not even be able to start the discharge. Whereas LaB6 is very easy to use, especially in labs. You don't have to be careful with oxygen. Having said that, it's less efficient, especially at the currents we run. Barium oxide runs at lower temperatures, which in terms of erosion is good. Okay, so just a few words to close. So grid ion engines is a technology that's existed for over half a century, but it's good to see that finally it's coming to especially the commercial market. It's quite exciting times for us. If you have to remember just a few things, so really it's that there's three independent processes: ionization, acceleration, and neutralization. Ionization will define what type of gridded ion engine you have, and acceleration is really the key. It defines what thrust and what ISP you're going to have. So the acceleration is generated by the grids, and again you always want to remember the child Langmuir Law, because that will give you all the indications you need when you think about designing a grid, or when you try to look at the limitations you have with a given grid. It's quite important. Okay, thank you very much.
Okay, we have time for some questions. Any question? Yeah.
The electrons that are emitted by the neutralizer have a few exchanges of energy. Why do you need then so large potential difference between the neutralizer and the acceleration grid that is of the order of 100, 200 volts?
Okay, so that's a good question. You're right, and if you just want to run at the beginning of life of the thruster, a few volts would be enough. Now what happens, there's two things. There's the fact that because you have an aperture, the voltage you apply on the grids is not the voltage you have in the middle. So there's always a drop in the middle of the grid. So what you want to make sure is that it's the voltage in the middle of the grid that is low enough. And then the other factor is erosion, is that you want to make sure that at end of life, when you've had erosion, that potential is still low enough to avoid electron backstreaming.
Okay, I have a question. Well, more than a question, a comment. Can you elaborate a little bit more about in the lifetime, for example, when you have charge exchange ions and the holes start to be bigger, then you have means to even if there is the performance starts to be bad, you can improve it again just because of the flexibility of the engine.
Yeah. I mean, to be fair, the life limiting factor on axle grids is usually pits and grooves, which is only a problem in terms of the structure of the grid. Even if you have a hole in the middle of the grid, which is very small, you can run the thruster. We've done it, and the performance is still very good. The only problem you have is if you completely lose the grid and you have a hole this size. So that's it. And I think what you were saying is the flexibility maybe on the discharge. I think that's...
Yeah, my comment more or less was, when you have the erosion of the grids and then the holes start to be much bigger, so the pressure change, and you can change this by increasing the mass flow. So if, for example, if we go to Mercury and something happened with the grids, we always have means to play with the different parameters to come to a performance that maybe is not the best, but still is good enough to do it. So the flexibility of the ion engine in flight is something really interesting.
Yeah.
It's difficult to lose an ion engine.
Yeah. I mean, the T6, for example, is so we always say it's a 5 kilowatt thruster, but it can throttle. Well, it can actually produce thrust anywhere between it's 25 or 30 millinewtons up to 200 millinewtons. Now, we don't operate there for BEPI, for example, because we have other requirements, but it's a very, very flexible discharge. Yeah.
So,
And what about the grid materials? What are you using now? And because I've always heard also you're working on carbon materials and even ALM.
Okay, yeah. So originally, most of the grids were always molybdenum, which is quite good. It's got erosion, a spotter yield that's quite low. But we have, so we still have molybdenum for the screen grid, but we have carbon for the axle to have even less erosion on the axle grid. There's some, so we're working on having a carbon-carbon grid to have also the screen grid in carbon. That's not easy to manufacture. So there's different techniques you can use to manufacture the carbon. There's what we call carbon-carbon or pyrolytic carbon, which is what we're looking at right now.
So I had another question on the grids. I always wonder what is the, if it is important, the attraction between the two grids because they are at a different potential. So probably at some point, if they are weak enough because of the pitch and groove, they will buckle and touch each other, and then that is the main mechanism of failure, or?
Not really, no. You mean from the electrostatic force, or?
Right.
Okay.
I mean, if it's important or not, or?
No, the electrostatic force is quite small actually. You can calculate that, and using the sort of applying a pressure and using a mechanical model, we've looked at that, and it's fairly small. What does affect though the distance between the grids is temperature, because what we do is define that distance between the grids when the thruster is cold. That's how we measure it. But then when you start the discharge, everything heats up, and you have a different expansion coefficient, and the distance changes. But it's we're talking about nothing.
Okay. If there is no more question, there's another question there.
So, when designing the size of the holes of the accelerator grid, so the transparency of the grid, the parameters you consider are the erosion and making the electrostatic field more or less constant, or is this something else?
Yes, so that's a good question.
Only those two. There are no more parameters.
No, not only. I mean, there's many other parameters that you have to consider. You have to consider the structural integrity of the grid. So it's a difficult question because what you want to do is it's fine. you want to maximize the transparency of your grid, okay? So you want to extract as much as possible. So you want them to be as big as possible. But also, you don't want them to be too big because of the child Langmuir Law. So that's one thing. Also, you have to keep in mind not only the plasma physics, but also the mechanical engineering. So you also want to make sure that when that grid is going to be launched and it's going to be shocked, it's going to survive. It's not just going to break. And that's the same for the thickness. You want a very thin grid, but you don't want it thin enough that it's just going to break. So it's not an easy answer, sorry.
Okay. So any other question? No? Okay, so we thank the speaker.